this particular video we are going to discuss about the generalized Ehrenfest theorem. In our one of the video I've discussed about the Ehrenfest theorem, but this video is going to be on the generalized Ehrenfest theorem, which means the format of that particular theorem, which is widely used and quite useful while describing some different phenomena in quantum mechanics, like when we study about the conservation of the momentum in the quantum mechanics. This format of the Ehrenfest theorem will help us. So let's try to derive out that particular format. So first of all, let's find out we have chosen our the quantity q. Now what we are going to do is that we are going to take the time derivative of this particular q. So taking the time derivative d by dt of this particular q. Here it is the sign of the expectation value, and here is our dynamical thing, so measurable thing. So d by dt of this particular q, and we are going to describe this particular expectation value of q in the Dirac notation, which I hope that you all know about the Dirac notation, that it's like the psi and here q psi. So this is the notations used used by Dirac to use this. So now what we are going to do is that we are going to take a time derivative. So this is not the time derivative, we are going to perform the time derivative of this particular thing. So let's see what will happen. So d by dt of your expectation value of q is equals to, performing this, it will be d psi divided by dt q psi plus psi dq by dt psi and plus psi q d psi by dt. So this is our particular expression. Now what we are going to do is that first of all we are going to write the wave equation. So new wave equation, which is iota h bar d psi by dt is equals to the Hamiltonian psi. So this is our first, and for the complex conjugate of this particular psi, we are going to do this by the negative iota h bar d psi by dt is equals to h psi. So this is two equation. Why? Because this first is for the normal part, and this is for the taking the complex conjugate of this particular wave function. So this is complex conjugate, that's why I have changed the sign iota, and here is the minus iota. So this is the complex conjugate. Now we are going to put it the value of d psi by dt into this particular expression. So let's see what will happen. So we are here with the time derivative. I'm not going to write it the time derivative all the way, I'm only going to write out the expression which is on the right side of our equation, which is here. So the d psi by dt is equals to the h psi, and here divided by negative of iota h bar. Here this is 1 minute. Here it will be h psi divided by negative here iota h bar, and here it will be q psi, and then here it will be h psi. 1 minute. Here it will be psi dq by dt psi, and plus here for our third part, which is psi d, sorry, here it will not dq by dt, I have written it, it will be then q and h psi divided by iota h bar, and this. So this is our expression. Now we are going to simplify this. How? So we are going to take out this particular iota h bar. So it will be negative negative will become positive here, so it will be iota here. So let me write it clearly. Here it will be iota by h bar, and here it will be h psi q psi plus, if you see this particular expression, this is the expectation value of the time derivative of the q operator, so it is nothing but just the expectation value of the time derivative of the q, and plus here this expression will be 1 upon I h bar. Okay, so let me convert it into the upper iota, which is negative. Here it will be then negative divided by h bar. Okay, and here it will be psi q, and here it will be h psi. So this is our expression. Now our expression will be iota by h bar h psi q psi, taking this as negative iota by h bar psi q h psi, and plus expectation value of the time derivative of the q. So here, if you see this particular thing carefully, it is nothing, it's just the expectation value of the commutation relationship between the h and the q operator, and this is equals to plus dq by dt expectation value. Now this is our generalized Ehrenfest theorem. So d by dt of the expectation value of q is equals to the iota divided by h bar, and expectation value of the commutation relationship hq, and here plus the expectation value of the time derivative of t. So this is the generalized Ehrenfest theorem, and it is very much useful, because one thing is important in this particular equation is that when any of this particular quantity q, the quantity can be momentum and all of that stuff, so whenever a quantity like here q commutes with h, what's the meaning of the commutes with h? The meaning is like that when I will do the commutation relationship between h and q, which is equals to hq minus qh, and when this is equals to 0, it means it commutes. Ultimately, when the value of the commutation relationship is 0, we say that the two operators commute with each other. So the fact is that when q commutes with the h, then q is a conserved quantity, and this is a base for the conservation of the momentum and all of that other quantities we are going to study next. So the next topic is going to be on the translation operator, and here we will study about the different types of the conservation principle, conservation of momentum, conservation of energy, that we done in the classical mechanics part. So the essence of this particular video is that whenever an of the variable q, when it commutes with h, it means it's a 0, commutation relationship is 0, then it is a conserved quantity. And using this particular Ehrenfest theorem, we are going to prove this particular same for the momentum operator and for the momentum in the next video. So this is for the today's video, and if you have any kind of doubt, you can write down in the comment section.